No, I gotta go back.
Okay. Bert, are you ready?
I'm ready.
I can. Okay, cool. So thanks for coming back. Before we start, I want to note that if you have any questions during the talk, please type them in the Q&A box located at the bottom of your Zoom window. Also, in the Q&A box, you can upvote questions that you think are particularly important. And at the end of the lecture, I will read out a few of the most popular questions to our speaker. So our second speaker today is Professor Bertrand Halperin from Harvard University. Bert is famous for many fundamental works in condensed matter physics, including the two-dimensional melting and quantum Hall effect. He will give a lecture on the quantum Hall effect in a partially full Landau level, quantized and unquantized. Thank you very much for being here, Bert. Now it's all your time, Bert.
Okay, thank you very much, Pengji. What I'm going to talk about today is it's related to Steve Simon's beautiful talk this morning, but not too closely. I'm going to be talking about quantum Hall effects, which of course are topological states of matter. They were perhaps the first topological state of matter to be really studied. Certainly the fractional quantum Hall effects are the first ones that were intrinsically many body, non-trivial states of matter. But I'm not going to be emphasizing topological concepts very much in what I'm talking about. And I will, the states I'll be talking about are essentially entirely abelian states. So they were the least interesting states in the language that Steve talked about. But you'll be hearing more, I'm sure, about non-abelian states later in this series. Other lecturers will talk about them. Also, in the spirit of the title of the summer school, I'm going to be talking a bit about excitations, not just about the ground states, and I will be talking about quite a bit about the effect of interactions and how this strongly correlated aspect of these systems are important. Whoops, no, wait a minute. Now we have a problem. Wait a minute. Okay, so the outline of my talk is that, first of all, I'm going to begin with a brief review of what the quantum Hall effects are, why they are, and why the quantized Hall effects are exact. I'm going to talk primarily about the fractional quantum Hall effect, not the integer one, though I'll briefly talk about that. The main question there will be, why does it exist at all? Not so much the topological aspects. I will also talk about something I call the unquantized Hall effect, which occurs at, say, Landau level filling fractions a half, where you don't get quantization, but there's still very interesting things going on. In this lecture, I'm only going to consider a single component electron gas. So that means that I'm going to talk about a single layer system, and I'm going to assume that all the electron spins are aligned with the magnetic field, so that there's not a spin variable to think about. And in the second lecture, I will talk about systems where there are two components, either spins or two layers. So to remind you about the basic measurement in a Hall geometry, which is slightly simpler perhaps than the geometry that Steve showed you. We have, in this case, a current flowing in the x direction. We measure the value of that current. We have, we're talking about two-dimensional electron systems, so that the field is in the plane, perpendicular to the plane. We have current flowing in the x direction, and we have contacts at the edges of the sample, which can measure the voltage in the X direction or the voltage in the Y direction. And the Hall resistance is defined as the voltage in the Y direction divided by the voltage in the X direction, whereas and then we can also define a longitudinal resistance, which is the voltage drop in the X direction parallel to the current. Let's see. I'm sorry, I seem like to have skipped a slide. Let me just go back to this for a second. Just to talk about the quantum Hall effects in general, they refer to a large set of peculiar phenomena that occur in two-dimensional electron systems, strong magnetic fields and low temperatures. Usually, these have been seen in semiconductor structures like electrons trapped in a thin layer of gallium arsenide surrounded by barriers of aluminum gallium arsenide. These are quantum wells, and they're basically high-quality transistors. They've also been studied extensively in graphene, and there are many phenomena in this regime of quantum Hall effects, which include the integer and fractional quantized Hall effects, the unquantized quantum Hall effect that I mentioned, and many other things like Wigner crystals, stripe formations, and so forth. But as I said, in this talk, I'm going to be primarily focusing on the fractional quantized Hall effect and the unquantized quantum Hall effect. Okay, so to return to the Hall geometry, I apologize for the disorder here. So what was discovered in 1980 by Klitzing and his coworkers was that if you measure the Hall resistance, Vy over Ix, in one of these samples at low temperatures under proper conditions, as you sweep the magnetic field, you see that there are a series of plateaus in the Hall conductor, regions of magnetic field where the Hall resistance doesn't vary at all, and it takes on a constant value. And at the same value of magnetic field, if you look at the longitudinal resistance, it's zero, or at least unmeasurably small. The thing that was even more remarkable is when you measured the values on these plateaus, if I looked at the Hall resistance, or it's a little easier to talk about the Hall conductance, which is 1 over the Hall resistance, it has a very simple formula, namely it's a rational number. Well, originally it was an integer, nu, times e squared over h, where e squared over h is the electric charge squared divided by Planck's constant. And that's a number that corresponds to 25,812.02 ohms. And this is independent of the precise shape of the sample, the choice of material, et cetera. And it's been shown to hold on the order of a part in 10 to the 9th or 10 to the 10th between different samples under proper conditions. And then even more remarkable, the fractional quantized Hall effect, which was discovered 2 years later in very high quality samples in a strong magnetic field. You find additional plateaus in addition to the integers, where the Hall conductance has the form nu e squared over h, where nu is now a simple rational fraction, usually with odd denominators. So the original ones were 1/3 and 2/3. Then after that, there was 4/3, 5/3, 1/5, 4/7, 5/9, many others, almost all with odd denominators. In general, for most even denominator fractions, including the simplest even denominator fraction at nu equals 1/2, you do not observe any quantized Hall plateau at all. When you go through that value of the corresponding value of the Hall conductance, you find that the Hall conductance just varies smoothly, more or less linearly, with the applied magnetic field, and the resistance Rxx is not zero, but it's some constant value that depends on the sample, and it varies smoothly. So it looks like it's really very dull. But on the other hand, it was found that there are strong anomalies in other properties, not in the simple transport, but if you look at surface acoustic wave velocity, for example, as experiments were done in around 1990, they found something very strange occurring close to this nu equals 1/2. And that's what I call this unquantized quantum Hall effect. And this just shows you, this is a plot from 1987 showing the fractional quantized Hall states. This is the Hall resistance again. Here's a plateau at nu equals 1. There's nu equals 2, 3, and here you see the fractions which are labeled by the value of nu, 4/5, 2/3, 5/9, and so forth. And you can see the corresponding dips in the ordinary resistance, and you can see it where nu equals 1/2 should be. You're passing through that value. You have just sort of a flat, kind of featureless, broad feature in the resistance, the longitudinal resistance. Now, I should say that some even denominated quantized Hall states have been seen, in particular at filling fraction corresponding to nu equals 5/2 and 7/2. There is something which is rather different. The nature of this plateau is still a matter of debate. It's certainly active current research, and I'm not going to talk about it here. I think Dima Feldman will talk about it in his talk, and perhaps other people as well. These are states that are supposed to be non-abelian. Okay, so what are the conditions for a quantized Hall effect, either integer or fractional? Whoops, sorry, we went. So basically, what you need is that if you have an ideal bulk, which it has, say, it has no impurities, and you look far from the edges, the system should have an energy gap for the creation of any kind of mobile electric charges. Now, in the presence of impurities, there can be states in the energy gap, but they should be localized states, so that at low temperatures, any carriers present will freeze out onto these localized states, and they don't move in the presence of an applied electric field, and they don't affect the transport properties. In particular, what happens, therefore, is the bulk is essentially an insulator, or more precisely, what happens is that in the absence of mobile states at the Fermi level, there cannot be any electric current flowing parallel to an applied electric field. You can have currents flowing perpendicular to the electric magnetic field, which are Hall currents, come from states below the Fermi surface. Now, although the energy gap will vanish, will be present in the bulk, it necessarily occurs for topological reasons that in these states there are the vanishing energy gaps along the edges. And what happens is that the edges are a particular kind of one-dimensional metal. It's called a chiral metal because over large length scales, charge carriers travel only in one direction along the edge. And the existence of these chiral edge states is something that's protected by topology, but I'm not going to say too much about it here. But it's essential. And what happens, therefore, is if you have a quantum Hall system which has a gate on top of it that screens out the electric field, and it's a large system, then you're going to find that there's no electric field in the bulk, and there'll be no electric currents in the bulk. Any current that does flow in such an experiment flows along the edge, and it can flow along the edge because you have these gapless excitations along the edge. And it turns out that the current along the edge is determined by the voltage along the edge, which is the electrochemical potential along the edge. Even if there's no electric field, there could be a difference in chemical potentials between the two edges, and that will produce a voltage difference. And then for small changes, at least in the voltage, the current that flows along a given edge is increased by an amount G times delta V, where G is a conductance, and this will be quantized, and this will determine the quantized Hall conductance. So the question is, if you accept this, and I ask you to accept this for the moment, the question is, how do you get an energy gap in a quantum Hall system, since that's the first thing we need in a bulk quantum Hall system? So of course, sorry, I'm having some trouble on my screen here. Okay, so get away here. Okay, so let's first talk about the integer quantum Hall effect. So let's remind you what happens if you have non-interacting electrons in a uniform magnetic field, B, in 2 dimensions. So in quantum mechanics, the energy levels in a magnetic field are quantized into Landau levels, which have energies h over 2 pi, or h bar times omega c times n plus a half, where n is an integer 0, 1, 2, 3, and so forth. These are just discrete levels, which are basically harmonic oscillator levels for circular orbits in these magnetic fields. But there are many, these orbits are very degenerate, of course. You can put the center of this orbit many different places, and it turns out that in each Landau level, the number of linearly independent orbitals is precisely equal to the number of flux quanta threading the system. So that means it's magnetic field times the electric charge times the area divided by Planck's constant in standard units. So it's conventional to define a Landau level filling fraction, F, which is the ratio between the number of electrons and the number of flux quanta, which is just equal to the density of electrons divided by the magnetic field in units of h over e. And if F is an integer, then that means the system will have an integer number of filled Landau levels. If it has an integer number of filled Landau levels, then the Fermi level will be in the gap between them, and we can be in a quantized Hall system. Okay. Now, in that case, remember, if we have electrons in a uniform positive background with no impurities, the Hall conductivity, we know, is given by it's an exact result that just follows from Lorentz invariance, basically, that the Hall conductance is going to be E times the density of electrons divided by B, which is just equal to this Landau level filling fraction in units of this magic quantum E squared over H. So if there exists an energy gap at some magic value of the filling fraction, and if the chemical potential is inside the gap, then NE is locked to be, as long as the chemical potential remains inside the gap, the density will vary as you vary the magnetic fields over some range of B. And in that case, the conductivity will be locked at a value nu times E squared over H, where nu is just this filling fraction, this magic filling fraction S of S. And this will happen, as we can see, for non-interacting electrons when F is an integer. But if we can produce somehow an energy gap that's locked to some magic fraction other than an integer, then we could get a fractional quantized Hall effect. Now, why is this? This is true for ideal electrons. Why is it still true that the quantization remains exact in the presence of impurities and the sample edges? That's a question that I'm going to defer. I hope I'll get to it at the end of the talk, but that does boil down to topology in some sense. Okay, so fractional quantized Hall states, which is the main subject of my talk. The Fermi level is in that case not between two Landau levels, but it's the middle of a partially filled Landau level. So if you had non-interacting electrons, the ground state would be extremely highly degenerate, and you can fill these orbits in lots of different ways. And certainly there'd be no energy gap in that case. So clearly, electron-electron interactions are essential to produce an energy gap. And since or if you're inside one of these Landau levels and all the states are degenerate, the kinetic energy essentially vanishes. Everything is dominated by potential energy. So this is certainly a strongly interacting system. And the traditional starting point for understanding these fractional quantum Hall states, well, there's several of them. There's the basis of using trial wave functions and something I call Fermion-Chern-Simons theory. Now, trial wave functions, the first one was introduced by Laughlin in his brilliant paper in 1983, which explained how you would get, how it gave you some understanding of how you would get fractional quantum Hall states at filling fractions nu of the form 1 over 2n plus 1, where n is an integer. So this is 1 over an odd integer, arbitrary odd integer. And Jane, in 1989, generalized these trial wave functions in a way that which he called composite fermions, wave functions that he called composite fermion wave functions, which gave him a way of sort of explaining quantum Hall states of the fraction of the form nu equals p over 2n p plus 1, where n and p are again integers. N can be is a positive integer, p can be the positive or negative, and these again are fractions. As you can see, there'll always be fractions with odd denominator, but not all fractions of odd denominator can be explained this way. But the most prominent ones, such as the ones we saw that on the experimental graph, most readily, those are indeed of this Jane form, and primarily they're with the case where n is equal to 1. So it's p over 2p plus 1. The fermion-Chern-Simons theory is a theory which was introduced by, it's a way of looking at things that was, well, at least to a large extent, introduced by Lopez and Fratkin. It existed before that, but they used it extensively to describe, as an alternate way of describing Jane's composite fermions and trying to understand better what's going on there, and also to understand the transport and excitation properties in these states. And what these amount to, they're not trial wave functions, but it's a transformation that converts the electrons into a system of fermions interacting with what's called a Chern-Simons gauge field. And I will certainly talk about just what these things are. So let's begin with the trial wave functions. So first of all, let me assume that the electron-electron interactions are weak compared to the splitting between Landau levels, which would happen, if, for example, if the mass of the electron, effective mass, is very small. And under such conditions, you can neglect the mixing. If you have a partially filled Landau level, you can neglect the mixing between Landau levels. Electrons in a Landau level can scatter off each other, but they won't. They'll stay within the Landau level, and they'll just go to different states within the same Landau level. And here I'm going to assume that we're in the lowest Landau level, which means that we're talking about filling fractions less than 1. And it can be shown that if you're in the lowest Landau level, wave functions must have the form, which if I work in a circular gauge, where the vector potential is in a circular direction, then the wave function for n electrons can be written as the form of a polynomial of a function p of z times the product of j from 1 to n of a Gaussian factor e to the minus zj squared, absolute value, over 4 lb squared, where lb is the magnetic length, which is the inverse square root of the electric field, of the magnetic field, times E over h bar. And z is x plus iy. It's a position of the electron in complex notation. And p, this factor p, is either a polynomial or more generally it has to be an analytic function of these zj's. Otherwise, you're not in the lowest Landau level, and that would cost you a very large amount of kinetic energy. But any state that's of this form has the lowest possible kinetic energy, and then you just have to minimize what's going on with respect to potential energy. And this z plus the x plus I is for when EB is greater than 0. If you have magnetic field, if EB is negative, then you have to use x minus IY. Okay, the simplest case is Laughlin's wave function, or for filling fraction 1 over 2n plus 1. And there, what Laughlin did is let's just choose this polynomial to be simply a product I less than j, zi minus zj, the separation between the two particles in complex notation, raised to the power 2n plus 1. And he was able to show that in this case, the electrons form a disk, which is centered at the origin. The area of the disk is proportional to the number of electrons. The disk will have a uniform density, and the filling fraction, the density divided by the magnetic field, will just be of the form F equals 1 over 2n plus 1. In the case where Yeah, okay, right. So if n is equal to 0, then this is just a filled Landau level. Otherwise, it's a fractionally filled Landau level. And it turns out you can show it's the exact ground state in the limit of short range repulsive interactions. It turns out that it has very good overlap with the ground state when you have Coulomb interactions, which are not very short range, as determined by calculations in finite systems. That's the only way you can really check it. It works very well on systems that they're often carried out on a sphere or on a torus. You have to generalize the wave function slightly. So you have this very good wave function for the ground state, and indeed it appears that we know that it's an exact wave function for the ground state. We know that excited states have different energies, and what's not known rigorously but shown very well by calculations on finite systems, at least, is that there's a finite energy gap. There's a gap that remains finite in the limit of an infinitely large system. The gap in the case of filling fraction 1/3 is of the order of 1/10 of the energy, the fundamental energy E squared divided by the magnetic length LB. Okay, and these Jane's generalization of these states at his filling fractions P over 2n P plus 1 was to say, well, let's try a wave function which has the form of an operator PLL, which is the projection operator onto the lowest Landau level, times a Jastrow factor J sub n, which is just the product of Zi minus Zj to the power 2n, times a wave function, this psi p, which is the wave function of P filled Landau levels for P greater than 0, which corresponds to fractions less than a half, or it's the complex conjugate of that wave function for the absolute value of P filled Landau levels when P is less than 0. That corresponds to fractions nu greater than a half. So this JZ, of course, would be okay in the lowest Landau level. It's an analytic function, but these functions are not analytic functions times Gaussian, so they're not in the lowest Landau level, and you have to apply this operator to project them down to the lowest Landau level to get something that's the lowest Landau level. This is not an easy thing to do, but Jane has tricks for trying to evaluate at least approximately these wave functions, and for reasons that I guess are not really very well understood, they seem to agree very well with what is observed in finite systems. They have a tremendously good overlap. So they seem to be very good starting states. And as I said, with examples for n equals 1, as you let P go 1, 2, 3, you get a series of fractions 1/3, 2/5, 3/7, which converge to 1/2 from below. And P equals -1, -2, you get fractions like 1, 2/3, 3/5, 4/7, which converge from above. So as I say, why they have very good overlap is not so easy to explain. I don't think there's really any good explanation for it, and I won't try to explain it. What I'd like to do instead is turn to this Fermion-Chern-Simons formalism, which at least gives some alternate way of seeing why this might work. And as I said, this was employed by Lopez and Fradkin to describe dynamic properties of Jane states. And Patrick Lee, Nick Reed, and myself used it in 1993 to study this unquantized state at filling fraction 1/2. So this begins with a unitary transformation, as I said, which is a generalized gauge transformation. So we take the ground state, let's say, of the electrons, or any eigenstate of the Hamiltonian of the electrons for in the magnetic field, and we multiply it by a phase factor, which is a product of all I less than j, the Zi minus Zj divided by the absolute value of Zi minus Zj, so it's a pure phase factor, raised to power 2n, where n is an arbitrary positive integer. I will almost entirely use n equals 1 in this case. So now, if the original Hamiltonian is a simple Hamiltonian, which I write as a kinetic energy term and a potential energy term, here I've used units where E is equal to -1. So this is the momentum of the ith electron. This is the vector potential of the ith at the position of the ith electron, the vector potential felt by the ith electron at its position. M is the effective mass. And this is a two-body interaction that just depends on the positions of the particles. Then when you make the transformation, a gauge transformation in the wave function, you have to make a corresponding unitary transformation on the Hamiltonian. And what comes out is the same Hamiltonian as before, except you have to add to the kinetic energy a term a sub I, little a sub I, which is depends on the position of all the other electrons in the system. And it has the form, there's a 2n in front, sum on all the other electrons. Z is a unit vector perpendicular to the plane, cross product with Ri minus J over Ri minus Rj squared. And this is just the vector potential you would get from a solenoid with flux quanta, with 2n flux quanta placed at the position of the jth electron. Okay, so it's a solenoidal vector potential for each electron. This you can take the curl of this vector potential, and we would call the Chern-Simons magnetic field. This is called the Chern-Simons vector potential, by the way, and this curl is the magnetic field. And you can see if I take the curl of that, I'm going to get the divergence of the density of this quantity, and it'll turn out to be just, since there's just one flux quantum for each located at two flux quanta located at each charge, this magnetic field is equal to 4 pi in these units, which is 2 flux quanta, times the density of electrons, where there's an operator that has a delta function in the position of every other electron. And the other important point is that if 2n if 2n is an even integer, then when I interchange two electrons, if in the original electron I picked up a minus sign, I pick up the same minus sign in the transform case. So I'm still dealing with fermions in this effective Hamiltonian. And this is called a Chern-Simons potential, because if in a Lagrangian formalism, you can derive this Chern-Simons interaction by including a term in the Hamiltonian that is of the so-called Chern-Simons form, which is epsilon mu nu lambda a mu derivative d nu a lambda over 8 pi, where d nu is the derivative in the direction, the spatial derivative in the direction nu, and this is the epsilon is the unit anti-symmetric tensor. But I will not use that in here. Okay, now, so far I've just transformed one impossible problem into another problem that can't be solved exactly, but the advantage is now we can, I'm in a position to make a mean field approximation on this, which makes a lot of sense. It's a Hartree approximation, whereas if you try to make a mean field approximation to the original system, you get completely the wrong answer. So what we want to do in a mean field approximation is we're going to replace this true Chern-Simons magnetic field B, which depends on the positions of all the electrons, by just its average value. And the average value is just, in the case where n is equal to 1, where I'm just attaching two flux quanta, it's just equal to 4 pi times the density, the average density of electrons, Ne. And the other thing in mean field is you replace the two-body Coulomb interaction by just the average electrostatic potential, which in a homogeneous system is just a constant, and you can choose that constant equal to 0. So what we get is something very simple. It's free fermions moving in an effective magnetic field, which is, because of the negative sign of the electron, it's B minus 4 pi Ne. Delta B is B minus 4 pi Ne. And so I could define an effective filling fraction, P, which is 2 pi Ne over delta B, which is completely analogous to the original filling fraction, which was 2 pi Ne over B. And now by simple algebra, I can relate these to each other. And what you find is that F is equal to P divided by 2P plus 1. Okay, that's just simple algebra. Now, what happens if P is an integer, either positive or negative? Well, then in mean field theory, of course, you say, well, we have integer number of filled Landau levels in the effective magnetic field. So there should be some kind of energy gap, which would be the cyclotron energy in the effective magnetic field. That would be basically, instead of B, it's delta B over M in these units. And that would be 4 pi NE over M times P. So the larger P, the smaller this gap, but it's still just down by a factor of P. And but it's still a gap. And so you say, okay, if the mean field theory is right, and the original system, and the system is stable, it has a gap, then the original electron system, it should be also stable, and it has a gap, but the filling fraction is not 1 over P, is not P, but it's P over 2P plus 1. So that would explain why you're getting, if this is right, that's why you would get filling fractions at quantized Hall states. Okay, fractional quantized Hall states. So what happens if I set F equals a half, which actually is the limit of P going to infinity? So in that case, I have 2 flux quanta of the actual magnetic field per electron. That's a definition of F equals a half. And that's exactly canceled by the Chern-Simons field. So the effective magnetic field is B minus the average of B is 0. So if in that case, the mean field theory is not a bunch of filled Fermi. The mean field ground state is just a filled Fermi C with a radius KF, which is equal to 4 pi NE to the 1/2. It's 4 pi rather than 2 pi, which you would get for an ordinary electron system, because we have only one spin state that we're considering. Now, if this is correct, then of course there wouldn't be an energy gap at filling fraction a half, and there shouldn't be a quantized Hall state. On the other hand, what you might hope to do is be able to calculate all properties of the nu equals 1/2 state using perturbation theory, starting from this mean field state. The mean field state, of course, is not the exact state. And these perturbations, if you want to put the perturbations in, you have to include, of course, the effects of the fact that the two-body potential is not just a constant, but you also have to put back the fluctuations in the Chern-Simons field. The actual Chern-Simons field is not just its average field, but you have to include this delta B, which is the difference between the fluctuating field, the fluctuating particle density, and B. And it turns out that these fluctuations are actually crucial for calculating transport and dynamic properties. And also they are completely important for understanding the energy scale for the excitations. The energy gap, for example, is not given by the bare mass, but you have to renormalize the mass. So these gauge fields have very big quantitative effects, but qualitatively, it turns out that this mean field theory, or when properly handled, works pretty well. So why should perturbation theory work in this case? Well, for the quantized Hall states, where the mean field theory already predicts an energy gap between the ground state and excited states, it's at least plausible that if I put on the real perturbation, the perturbation theory, it may still converge because we have an energy gap. And if the perturbation is not too strong, maybe it won't destroy the energy gap and change the character of the ground state. And then, in other words, we would find that fluctuations will change the energy gap. They may reduce it significantly, but not generally drive it to 0. And if that's the case, then we should be in the same, we'd have something that's topologically connected to this mean field theory and should have very similar properties. It's very hard to prove that that's the correct case for any microscopic Hamiltonian, but numerically that seems to work pretty well, and it helps understand why Jane states work, since it predicts, of course, the same energy states as Jane states. But what about nu equals a half, where there is no energy gap? Well, then we can turn to Landau's theory of Fermi liquids. For ordinary interacting Fermi liquids in 3 dimension, no magnetic field, as Landau pointed out, they can behave, even though there's no energy gap there, they can behave in many ways like weakly interacting fermions. Elementary excitations are quasiparticles, just like weakly interacting fermions, which they have well-defined momenta. They're related adiabatically, in some sense, to the original fermions, but they have renormalized effective masses. And what happens is that you have low energy excitations, quasiparticles, that they call, that have lifetimes very long compared to their energy. When they have momentum close to the Fermi surface, you still have a sharp Fermi surface, and the volume of the Fermi surface is not renormalized. And there are some residual interactions between the quasiparticles. They're not zero, and they're important for collective responses to an electric external perturbation. So if, for example, if you want to look at what happens, what's the susceptibility when you apply a magnetic field coupling to the spins, or for dynamics, you can get things like collective modes such as zero sound from these things, from these interactions. But the ground state is still rather surprisingly well described by weakly interacting systems. And the reason that perturbation works well in that case is that even though there's no energy gap in the unperturbed system, the density of states for low energy particle hole excitations is very small at low energies, because you have to have both the particle and the hole close to the Fermi surface, and there's not much phase space for it. So if the interactions are not too strong and not too singular at small momentum transfer, the scattering of low energy particles can be very small, and that justifies the Fermi liquid theory. But it's still delicate, because Fermi liquid theory, since it's gapless, it can be unstable. And in particular, as you know, if you have attractive interactions, they lead to an energy gap, formation of an energy gap, and to superconductivity, which has properties which are quite different from the non-interacting Fermi liquid. So what about it for this composite Fermi liquid at a filling fraction of half? So in this case, we have, in addition to the Coulomb interactions, we have these Chern-Simons gauge transformations, which are really singular at small momentum transfer. And we find in that case that it really does have properties that affect things. We find that a sharp Fermi surface can, and we believe does exist, but the Fermi liquid is kind of what we sometimes call a marginal Fermi liquid. The effective mass, m star, is actually predicted to diverge as you go to the Fermi surface. The divergence is only logarithmic, or square root of a logarithm, in the case where you have Coulomb long-range interactions. But in short-range interactions, it's actually stronger. So that's pretty bad. But nonetheless, the mean field theory is a reasonable starting point, and many of the collective modes look exactly like what you predict for the in the mean field theory. And as I mentioned before, at filling fractions like 5/2 and 7/2 in gallium arsenide, you do have an energy gap, apparently, and there are quantized Hall conductances. And we can sort of explain that by saying, well, okay, in the higher Landau levels, this would be the second Landau level, in that case, the interactions are such that you have attractive interactions, and p-wave pairing between composite fermions leads to a BCS-like p-wave state, and that would introduce an energy gap. The precise form of this pairing is under some debate, as I've said, and I'm not going to be talking about that here. Okay, so what about excitations and transport in fractional quantized Hall states at filling fraction of half? In fractional quantum Hall states and in the unquantized state at filling fraction of half. So let's first go to the fractional quantized Hall states. So, as you know, in that case, the elementary charge excitations, they're called quasiparticles, they actually have fractional electron charge and unconventional statistics. That is, there'll be either fractional statistics or even non-abelian statistics. And in particular, in the Jane states, which have fraction nu over p, p over q, where q is this, p and q are, well, where q is equal to 2np plus 1 in particular, then and q is an integer with an odd integer. It turns out that the elementary charge quasiparticles in this case have charge E star, which is the electric charge divided by q. So like at one, yeah, okay. So, and Q could be 3, 5, 7, and so forth. The way you understand this in the Jane picture is you can obtain a quasi-particle by saying, instead of having just a filled number of integer number of these pseudo Landau levels in the fake magnetic field, we add one more electron to the lowest unoccupied one. And now the effect of the Jastrow factor is that we have in the is to move. It has these 1 over r z minus zj I minus zj to the squared. It pushes other electrons away from the added electron, and it basically pushes E minus E star electrons away to the boundary of the system, leaving just a charge E star behind, where E is 1 over Q. And you get the same picture, you get the same understanding if you try to do this in the fermium Chern-Simons picture, because you get, when you're adding a quasi-particle, you're adding an electron plus, in the case of n equals 1, you're adding p flux quanta, or and more general np flux. It should be 2n. You're adding 2np flux quanta. That's an error. We're adding 2np flux quanta, and you get the same charge, it turns out. So that's a way of understanding fractional charge. Fractional statistics, in this case, as I said, in these cases, we're just going to be looking at abelian statistics. And as Steve Simon explained, that means basically if you interchange two identical quasi-particles that you've created, the wave function will pick up a phase factor which is not equal to plus or minus 1 as you would for fermions or bosons, but you pick up some complex phase factor. And indeed, in the Jane states, quasi-particles have abelian fractional statistics, which are always different from plus or minus 1, and are related to the denominator of the fraction. Now, it turns out that direct observation of these fractional statistics is rather difficult, although they can be shown really rigorously to exist. And they've only been achieved really this direct observation very recently at nu equals a third, and only at nu equals a third, in interference experiments by Nakamura et al. But the fractional statistics have many indirect consequences that are more easily observed. And on the other hand, fractional charge is a little easier to observe. It was observed originally in shot noise experiments, and more recently using a single electron transistor on a tip as a charge sensor. And you could actually charge, these were experiments in Amir Jacobi's group, for example, where they could actually see, as they varied conditions, jumps in the charge in some kind of a puddle or say underneath the tip, as 1/3 of an electric charge entered at nu equals a third, or 1/5 at 2/5 at filling fraction 2/5, and with some statistical averaging, 1/4 at nu equals 5/2. Okay, that's the charge excitations. What about neutral excitation modes in fractional quantized Hall states? So the lowest energy neutral modes are excitons, basically, which would be a bound state of a positive and negative quasi-particle some distance apart. And these states are often called magnetorotons. And the bound state, the magnetorotons, because they're neutral objects, they can travel in a magnetic field. Their momentum is both kx and ky commute with each other. They have a well-defined spectrum energy as a function of their wave vector k. And this spectrum will be gapped, of course, in a quantized Hall state. It doesn't necessarily have the minimum. In fact, it generally does not have its minimum at k equals 0, but they typically will have one or more minima at finite wave vectors k. These excitons, they have the property that they're a bound state of a positive and negative quasi-particle with some separation d between them. And the momentum k is always going to be, it will be precisely perpendicular to this separation d and proportional to it. And what happens for very large values of k is the distance between the quasi-particles becomes very large. So you're going to get a free quasiparticle, a positive quasiparticle and a negative quasiparticle far apart. And that's basically the definition of the energy gap in such a state. But when they get close together, because of the Coulomb interaction, they can be bound and the energy can be somewhat less than the energy gap. Okay, let me now turn to transport and dynamic properties in the fermion-Chern-Simons picture. So as I indicated, you have to include, if you want to really understand what's going on in fermion-Chern-Simons, you do have to include the gauge field. And the simplest way to include it is in a random phase approximation, which is basically time-dependent Hartree approximation. And in that case, what you have is the response to an external electromagnetic field is if you want to say calculate that, what you do is you treat the fermions as free fermions, not interacting particles, but interacting in a self-consistent electromagnetic field, just as in a Hartree approximation. But you have to include not only the Coulomb interaction, but the Chern-Simons fields. And that means if you have fluctuation in the density, it not only produces a Coulomb potential, it produces, of course, a fluctuation in the Chern-Simons magnetic field, which would be just 4 pi times the fluctuation in the charge density. And also, if you have a current flowing, local current flowing, it produces a Chern-Simons electric field, which is 4 pi in these units times z hat cross. In other words, it's located at the current, but in a direction perpendicular to the current. The electric field is perpendicular to the current. And what you have to do is self-consistently calculate these response functions. And what you find is something given by the so-called Jaffe-Regel rule, that what you want to do is basically add the resistivity tensor that you obtain from the composite fermions to a background resistivity from the Chern-Simons field, which I call here rho hat Chern-Simons. And this is calculated just from free electron theory in the applied magnetic field. And here, this Chern-Simons field, it's a pure off-diagonal field, a pure Hall field with strength 4 pi in the case where you have two flux quanta. It's two flux quanta per this 4 pi. And it's pure diagonal. There's no off-diagonal term, so it's non-dissipative. And when you add these together, you get, sure enough, if you're looking at, say, the DC response at the Jane fractions, p over 2p plus 1, you indeed get, as you must, the nu over 2 pi in these units, which is just nu over e squared over h for the off-diagonal elements, the Hall conductance, and 0 for the diagonal ones, as you expect. But you can also do this at filling fraction 1/2. And we can do it even in the presence of impurities. And what you get in that case is this, that the Hall conductance is still given, in this case, by 1 over 4 pi, which is 1/2 of e squared over h, what you would expect for non-interacting electrons at filling fraction 1/2, or for half-filled lambda level. But now if you have impurities present, and in the case of, if there were no impurities, the diagonal term would be 0, as is basically required by Lorentz invariance. But if you break this by putting in impurities, you get a finite mean free path for the composite fermions. And what happens is you get a Hall conductance, a longitudinal conductance, which is proportional to 1 over the mean free path for the composite fermions. So the fewer the impurities, the longer the mean free path, the smaller is this diagonal conductivity compared to the off-diagonal one. And you can also do this at finite wave vector. We can calculate, again using the Jaffe-Regel rule, the conductivity at finite wave vector. And what you find is a remarkable result that if we ignore impurities, the longitudinal conductivity vanishes as Q goes to 0, as it much, but it vanishes in a singular way. It's just the absolute value of the momentum divided by Kf with a universal coefficient, e squared over 4h, which doesn't depend on any details of the system. And this singular behavior reflects a non-local conductivity In real space, it's non-local, and it's because if you apply an electric field at one point, you get these composite fermions, which travel huge distances and get picked up by the electric field and produce a current far away. So this is a non-local behavior. In the presence of impurities, the mean free path cuts off this behavior, and sigma xx becomes local and independent of Q for Q less than this mean free path, which makes sense. But in a highly pure sample, you can pick up this Q dependence. And one consequence of this is that I self-consistently ask what happens in the absence of impurities if I put a long wavelength fluctuation in the electron density. You find that it relaxes anomalously slowly. In particular, if you have short-range interactions, instead of just having this excess density diffuse, it actually relaxes as the cube of the wave vector. For unscreened Coulomb interactions, it goes as Q squared, whereas you might have expected it to go as Q for an ordinary Fermi liquid in 2 dimensions. And this longitudinal conductivity can actually be measured in a surface acoustic waves experiment. And this is the explanation, basically, for the anomaly that was first seen by Willett and coworkers in 1990. And basically, you get an alteration in the velocity that's determined by the wave vector sigma xx, this conductivity sigma xx of Q at low frequencies. And the anomaly it really showed that these quasiparticles could travel in a straight line at nu equals a half at distances up to the order of a mean free path, or the wavelength of the phonon of the phonon, which is of order of a micron, which is about 100 times larger than the cyclotron radius for the electrons, which is the cyclotron radius is just the magnetic length in this magnetic field, which is a couple of 100 nanometers, 100th of a micron. Now you could ask, what happens if I go away from f equals a half, just slightly away? So in that case, the fermions see an effective magnetic field, delta B, which is the difference, B minus 4 pi NE, is the difference between the field at nu equals a half. And then you would think in the fermion-Chern-Simons picture, the fermions will now not move in straight lines, but they'll go in cyclotron orbits with a radius that's given by the cyclotron formula in this effective magnetic field. So it's given by h bar kf over the absolute value of E times delta B. And in the units where we set E and h bar equal to 1, this becomes kf over the absolute value of delta B. And of course, that radius gets bigger and bigger as delta B. This should have been kf over delta B. I apologize, a mistake. Kf over delta B. And of course, this will get bigger and bigger for B goes to, delta B goes to 0 for nu equals a half, but it's still finite, and it can be quite large. And so what we'll expect is that sigma x of Q will fall off when this cyclotron radius becomes smaller than this distance pi over Q, then the electrons won't travel that distance anymore, which corresponds to delta B being bigger than Q kf over pi. So at a given Q, the further away from delta B you can go, and the larger Q, the further away from delta B you can go and still see this anomaly. But what's more interesting is that if you go to the other regime where delta B is less than this QKF over pi, you find that it behaves in a non-monotonic way. And we actually predicted, one of the predictions of this HLR theory was that they would get maxima in this conductivity, sigma of Q, when this frequency, when this cyclotron radius was commensurate with the wavelength. More accurately, it becomes when it's pi times n plus a quarter divided by the wavelength, where n is an integer. That gives us this delta B is equal to QKF over pi times n plus a quarter. And you should see, in principle, in the absence of impurities, you'd see peaks at n equals 1, n equals 2, n equals 3, and so forth. And that gives you oscillations in the propagation of these as a function of magnetic field, gives you oscillations in the propagation of these surface acoustic waves, which we can think of in terms of this kind of commensurability oscillations. They occur, there are geometric resonances that occur when the cyclotron radius bears a certain radius to the wavelength. And those were seen by Willett in 1993 and were really a confirmation that we were on the right track with this fermion-Chern-Simons theory. And more recently, another way that this has been seen with much greater accuracy in more recent experiments in what we call Weiss oscillations. They're experiments in which you, instead of having a surface acoustic wave generating a finite wave vector, you actually deposit a set of lines on the top of the gallium arsenide, giving rise to a periodic potential with some wave vector Q, and you vary the magnetic field, and you can look for oscillations in the longitudinal resistance as you vary this magnetic field. And I know that you'll have a talk on this later in this, describing these beautiful experiments by Tamburov et al. In Professor Shayegin's talk later in this series. The last thing I want to mention is, again, returning to energy spectrum for these. Whoops, I misspelled Jane. I apologize here. It was late at night. For the, sorry, Janandra. The magnetic roton spectrum, the exciton spectrum in these Jane states near nu equals a half. As I said, there could be multiple oscillations, and these oscillations get more and more pronounced as you got closer and closer to Q equals a half. And this is a calculation, not an actual observation, of what the spectrum should look like very close to Q equals a half. This is at a fraction, well, but we could calculate this at 20/41 or 21/41. These are conjugate states, one slightly above and one slightly below nu equals a half. And the spectrum calculated in this self-consistent Hartree theory, taking into account both the Chern-Simons field with and without the Coulomb interaction, is given by this red curve here. And you see these oscillations. There are many more oscillations, but these are the lowest ones. This is Q is a reduced wave vector. It's the wave vector of the oscillation divided by basically the magnetic field deviation. And here's a reduced frequency. Okay, and this is basically formulas that came from a paper by Steve Simon and myself back in 1993. This is, the blue curve is what you would get if you just took into account the Chern-Simons field and didn't take into account the Coulomb field. So the Coulomb field is important, but the wiggles basically come from this Chern-Simons field. And there's no distinction between, you cannot see the difference between 2041 and 2141 in this curve. There's this particle hole symmetry about nu equals 1/2, which I will talk more about that next time. And the other thing is the minima of these dips. They correspond relatively accurate, not precisely, but quite closely to these commensurate positions, the values where the wavelength is commensurate with the wave vector and the cyclotron orbit are commensurate in the sense that I defined earlier. So this is quite closely related to these commensurability oscillations. Okay, I'm going to stop here. There are many references I could have given you, but instead I'll give a plug for a book. There are recent reviews of most of what I've talked about, and the extensive references to the original literature can be seen in chapters by Jane and myself in a book which just recently came out, Fractional Quantum Hall Effects, New Developments, which was edited by the two of us, appeared in World Scientific. I urge you to buy the book or have your library buy the book, but these chapters are both available on the archive. Okay, thank you very much, and I'm ready for questions.
Okay, great. Thank you so much, Bert. So we have many questions, so I will try to go through all of them. If you want to read them, you can click the Q&A button on your Zoom window, and then you can also view them.
Let's see if I can get
So, and I will just read them one by one. And
okay.
so the top is question is that is it well known if the composite Fermi liquid obeys or violates Latinger-Diequist theorem for all or certain feeding fractions?
So as far as we know, it obeys the Latinger theorem. There aren't that many measurements. The most accurate measurements are measurements by by Kamburov et al., which will be talked about in at some length, I think, in Mansour Shayagin's talk. There's some fine points that have to be made. So the definition of a Fermi wave vector is, strictly speaking, only defined precisely at nu equals a half. And of course, the measurements that are being made are slightly away from nu equals a half. And at nu equals a half, there's no question about how you define the Fermi wave vector. And from these Weiss oscillation measurements, in the limit of going to this nu equals a half, it seems that the wave vector that you would obtain from this analysis using commensurability seems to agree precisely with what you'd expect. Now, as you go slightly away from nu equals a half, to first order it agrees, and second order there are corrections. In fact, there's ambiguities in exactly how you're going to define. There are different ways of defining a Fermi wave vector. Just as in a strong magnetic field, you can define the density of electrons, but you don't have a Fermi surface. So there's some arbitrariness. And what I think you will hear from Professor Shayagin is that if you make the assumption that you try to identify the Fermi surface, the Fermi radius, with the density as being basically square root of 4 pi times the density of minority carriers. So it's electrons above nu equals a half and holes below nu equals a half. You get a very good fit, maybe, to his experiments. But theoretically, it's not clear that that difference makes what difference that means. But within the, I think in the limit of nu going to a half, it works very well. Furthermore, of course, I've just talked about the case where you have basically a circularly symmetric Fermi surface. Shayagin and company have looked at cases where the Fermi surface is anisotropic. It's beautiful work. The shape of the Fermi surface is renormalized, but the volume seems to be very well given by Latinger's theorem.
Yeah. So unfortunately, Shayagin is not going to give a talk in our analysis. Yeah, he will not. I mean, yeah, we have an update agenda and on the website. So the next question is: can one construct a diagrammatic, that is, green function approach to the composite Fermi liquid state of Gen?
Not that I'm aware of.
Okay. And the third question: can you explain again why mean field theory makes sense after consignment transformation, but not in the original program? As I see, after the transformation and replace the magnetic field with effective field, the problem looks the same.
Okay, well, this is easiest to explain in the case of a fractional quantized Hall effect. Let's see if I can, whoops, wait a minute. Okay, so in the case of a Jane state that's at filling fraction p equals 2p plus 1, you have we have in the transformed picture, it corresponds to p, an integer number of filled Fermi levels in this effective magnetic field. And so the ground state, it's clear what the ground state is. There's a unique ground state. And at least in the mean field theory, it has an energy gap. And since it has an energy gap, if you apply at least a weak perturbation, you can say, well, let's calculate corrections to the energy by first or second order perturbation theory, and we expand in powers of the interaction divided by this energy gap, and then you might get fourth order and higher order. And if you're lucky, at least, when you do the computation, you would expect that it will converge and the ground state won't be very much affected. And the excited states, again, they may be shifted in energy, but as long as there's an energy gap, they can be well protected. Now, if I didn't make the transformation, and then I just had, let's say, a 2/5 occupation, let's say that's p equals 2, a 2/5 occupation of a Landau level, and I ignore the electric field, then the non-interacting ground state is a 2/5 full Landau level, and I have enormous degeneracy. I can put the first electron anywhere as I want. In other words, you have to divide up. If I have n electrons, I have 2/5 n occupied states and 3/5 n filled states, and I can divide these up by 3/5 n by n choose 2/5 different ways. It's some enormous, exponentially large number of states, and they're all degenerate. So if I introduced perturbation theory, of course, I wouldn't know where to begin. You could try doing Hartree-Fock, and in Hartree-Fock, you can derive some ground states, which would be things like charge density waves. And they're reasonable guesses, but they turn out not to be the correct ones. You could do Hartree-Fock and look at some broken symmetry state in which you basically impose some, you break the symmetry artificially by putting on a charge density wave or putting on puddles and stuff like that. And that actually does seem to work in high Landau levels, but in the lowest Landau level, it just doesn't give the correct answer. It gives charge density waves, but the composite fermion state, the quantized Hall states have a lower energy. So you're out of luck.
Yeah. So thank you. For the next question is from Song Yang. Should the low energy states near 1/2 or not at 1/2 be viewed as excitations of composite Fermi and Fermi C, or excitations of nearby fractional quantum Hall states like 4-9? What is the phase transition between composite Fermi and Fermi C and fractional quantum states? Is there any order parameter?
Okay, so what we believe is, let's start at nu equals 1/2. I think is the question. And what happens if you go away from nu equals 1/2? Yeah. So if you had an ideal system which was infinitely large and no impurities, we believe there'd be an infinite number of fractions of this form p over 2p plus 1, which converge on either side. So there would be an infinite number of Jane states close by, and if you varied the density, what would happen is these states would all be stable, and if you varied the density, you'd go through a bunch of transition. Basically, if you were at some density in between, let's say a state with let's say let's say a state 20 over 41 and 21 over 43, you would phase separate. What would happen is that the system would phase separate into pieces, and the stable states would break up into regions, at least with short range interaction. With long range interactions, it can't quite phase separate, but you'd get very large regions which were effectively in one and then large regions were effectively another, you get some kind of complicated broken symmetry, translational symmetry state. That's what we believe. But of course, as soon as you introduce impurities or inhomogeneities, that gets wiped out. And then, or if you go to finite temperature, the energy gaps get very small. So if I go to some finite temperature, which is still very small compared to the effective Fermi energy, or the Coulomb energies, but still large compared to these minuscule gaps, it's going to look just like you were at nu equals a half with some extra composite fermions floating around, which is the same, so at finite temperatures, it gets smoothed out, and the nu equals 1/2 really governs what happens over a finite range, or in presence of impurities, it really governs what happens at a finite range. But ideally, you could get these infinite number of phases.
Yeah. So next question is, does Zeeman splitting play some roles at fractional quantum Hall effect?
Okay, could you repeat it again? I didn't.
Zeeman splitting.
Oh,
does Zeeman splitting play some roles at
yes,
fractional quantum Hall state?
yes, and I'm going to talk about that next time.
Okay, cool.
Stay tuned for tomorrow afternoon.
So next one is from Xiaomeng. So hi Bert, the partially filled Landau level have quench kinetic energy. How do I understand the kinetic energy or dispersion or effective mass of conversive Fermi liquid?
Yes, good, very good. Okay, so this is a little bit of semantics. So when I said the kinetic energy has zero, I mean, by kinetic energy, I just meant the contribution to the energy from the kinetic energy term when you project onto the lowest Landau level. But projection onto the lowest Landau level does have a drastic effect on the interactions, on the potential energy term. So what happens there is that ordinarily you would write out, you could Fourier transform a two-body interaction, and you get something which would be a sum over wave vectors of some the electron density at wave vector q times the electron density at wave vector q minus q, and you multiply by some coefficient v of q, and you sum up over all q, and all these states commute with each other, so you can try to solve them all at once. But once you project onto the lowest Landau level, these states with different the wave vectors density operate at different q don't commute with each other anymore. So this potential energy, which looks simple, is actually very complicated. And because the states don't commute with each other, it means that if I put an electron in one place, I put a pair of electrons, let's say, some distance apart, and they're interacting with the energy the energy depends on the separation, but that doesn't commute with the Hamiltonian, so it doesn't remain constant. They can move around. Basically, if you have a bunch of electrons, because the positions of two electrons don't commute with the positions of other electrons, it can generate time dependence and motion. Okay. And that's what.
So next question, could you elaborate a bit on the indirect consequence of fractional statistics?
Let's see. Yeah, so the indirect consequence, well, one of the consequences is that, and one of the things that led us to it at the beginning was that if you want to understand the, let's say, the 2/5 state, by saying, let's start with the 1/3 state and add electrons to the 1/3 state until it gets into the 2/5 state. Well, if I add an electron to the 1/3 state, it should break up into particles that have charge 1/3, quasiparticles. So I'm adding a bunch of these quasiparticles, and I add more and more of them, and then I should be able to describe them in terms of some kind of pseudo wave function that describes just I ignore the positions of all the background electrons and just keep track of the positions of these quasiparticles. And it turns out that indeed, if you do that and you write down a wave function in terms of the quasiparticles, when you add just the right number of charged quasiparticles to get to the filling fraction 2/5, what you can do is if you put in the fractional statistics that's predicted from you find that you can form a Laughlin-like wave function where you instead of being a product of zi minus zj to the power 3, it's some other fractional power, which is the power you would need for fractional statistics, and that gives you exactly the right answer. In other words, assuming that you're working with at nu equals a third, assuming that you're working with charges of 1/3 and with fractional statistics that have a phase angle of basically 2 pi over 3, I'm sorry, then if you form a Laughlin wave function and you fill it up with just the right number of quasiparticles, you get a 2/5 state out. So you can say that gives you a way of explaining the 2/5 state. That's one of the indirect consequences.
Yeah. So next one, why can the trial function be written in that way? I think he or she indicates the Laughlin wave function.
Why why is the Laughlin wave function good, you mean?
Can be written in that way. So
as which way?
I think it's the it's the function that it is written in the Laughlin wave function. Why it is written out?
This one, you mean?
Yeah, yeah.
Well, that's what Laughlin guessed. It was a guess, but
yeah,
it turned out that guess is a beautiful guess.
Yeah.
He guessed it by studying he studied the exact ground state for 2 electrons and 3 electrons. So he had reason for guessing it. He had a lot of reasons, and then he justified it. And he showed when you made this guess that it had remarkable properties. Namely, he showed that it indeed formed a filling fraction exactly what you wanted at 1 over an odd integer, and it's a unique simple wave function. And I think I may have pointed out to him that it's really the right thing to think about for short wavelength, for short distances, because this wave function vanishes. Let's say we have n equals 1, so it's zi minus zj cubed. So the wave function vanishes when 2 particles come together as the cube of the separation, or the square of it vanishes as the 6th power. Now, the Pauli principle only requires that it vanishes linearly. So by vanishing as the 6th power, it really keeps the wave functions apart. And that means for short range interactions, you're really going to do very well. And almost any other guess that you make, you have to have a certain number of zeros in the wave function. And this has the right number of zeros. And if I don't have it vanish as the 3rd power of zi minus zj when 2 particles come together, I have to put zeros elsewhere. But those zeros are wasted. These zeros keep the electrons apart. So you can see that this is really the best thing you can think of for short range interactions. And then Haldane showed this in a more rigorous way by looking at wave functions on a sphere. And as I say, it's somewhat of a guess that there's a finite energy gap, but you can see why this is going to be the exact ground state for short range interactions. And if there is an energy gap, then you would expect introducing Coulomb interactions might not be so bad, because by perturbation theory, the difference between short range interactions and long range interactions should be just a convergent perturbation.
Yeah. Okay, so due to a time limit, we should end at this moment. And for the rest of question, I will send to Bert and see if you have some time to answer it or not. And so I will hand over to the next host for the next speaker. So thank you so much for Bert, and we're looking forward to your next talk tomorrow.